Okay, so now that we've got our data from the Alka Seltzer lab, well, I've written down the one from number 1, experiment 1. I've written down the number from experiment 8, and we're going to use those numbers to finish the table, and then of course you've got the other ones from the second video. Remember, it was a reaction between sodium bicarbonate, which is the Alka-Seltzer, and acetic acid, which is well known as vinegar. We were changing the amount of vinegar, the acetic acid. This number was increasing, and then the amount of water was decreasing. That was kind of the control. So the first experiment, the mass of the flask and liquid going in, plus the tablet itself, this is everything going in. Conservation of mass says that should come out, but it doesn't. It's a little bit less because, of course, we produce some, this reaction actually produces carbonic acid. Carbonic acid splits into water and carbon dioxide. The carbon dioxide bubbles out, and then the mass appears to decrease. So we can tell exactly how much carbon dioxide was made. We can get column E now by subtracting these two. And we can do this all across the board. So C minus D gives you E. So I'm going to do that. I'm going to do it very carefully. 139.24 minus 138.79. I don't expect there to be a big difference. I get 0.45. And that's, of course, grams. That's my grams of carbon dioxide. So now, here's the question. How do we go from that to the next column, the mass of sodium bicarbonate used? Well, it turns out to go from grams of one chemical to grams of another, you need to do stoichiometry. All right? So now, remember, we should have balanced this equation. We had the whole equation on the board. You should have seen it on your lab. You should have balanced it by now. And you should have found that, in fact, well, there's one sodium there, one sodium there. There's 1, 2, 3, 4, 5 hydrogen over here on this side. There's 1, 2, 3, 4, 5 hydrogen on that side. There's 1, 2, 3 carbons on this side, 1, 2, 3 carbons on that side, and 1, 2, 3, 4, 5 oxygen on this side. 1, 2, 3, 4, 5. Well, it's, you know what, it's balanced. If it's balanced the way that it's written, then all the coefficients are 1. If the coefficients are all 1, then that makes your calculation easier because all the mole ratios are going to be 1 over 1. So if I'm going to start with the 0.45 grams of CO2, well, I need to turn that into moles of CO2. I don't want to calculate the molar mass for you. I want you to calculate the molar mass of CO2. I'm just going to use a made-up molar mass, but let's say, well, you know, that's going to be in the range. I'm just going to give us 50 grams per mole. I'm just going to make that one up. I want you to calculate the real molar mass. So let's say it was 50. Well then, okay, that would be the grams. Well then, this is grams, so then grams need to go on the bottom. Let's say 50, let's say it's 0.00, 50.00 grams over 1 mole. Okay, that would be the molar mass, and let's say this is CO2. Again, I just made this one up, but it's similar to what you're doing, just with the real molar mass. And now I can see when I divide 0.45 by 50, I'm going to get a really small number. I'm going to get a very small number of grams. I'm going to get 0.45 divided by 50 equals, I'm going to write it over here, 0.009 moles of CO2. Okay? So because the grams will cancel, so I'll have moles of CO2. Then what I need to do is jump between chemicals. I've got my key. This is my key. I need to jump between chemicals. I want to use the mole ratio. And the mole ratio, of course, is moles over moles. And because everything in this equation has a coefficient of 1, we know it's going to be 1 over 1, 1 over 1, and the CO2 would go on the bottom, and the NaHCO3 would go on the top. So it's going to be the same number, isn't it? times 1 divided by 1, it's going to be the same number, 0.009 moles of NaHCO3. So now if I want to get what goes there, I have to turn this moles back into grams. Well, again, I don't want to give you the molar mass for this chemical, but I can see this one's bigger because it's got the same number of carbon, it's got even more oxygen, and it's got sodium and hydrogen. I'm just going to give this a bigger number. I'm just going to give it 100 grams per mole. Now that's not the real molar mass, but you're going to calculate the real molar mass. Okay? And then now if I've got moles on the moles there, I've got to put moles on the bottom. So 1 mole of NaHCO3. I'm going to run out of space here. Okay, and then the grams, I'm just going to use the 100. Well, the grams are going to have to go on the top of NaHCO3. So notice that's the molar mass. It's the grams per mole. This was a molar mass upside down. And then, so it's this times 100. So I've still got this on my calculator. Times 100 equals 0.90. So I can write that in here now. 0.90. Now because I chose 50 and 100, we'll notice the molar mass came out to be double. And not the molar mass came out to be double, the grams came out to be double. So why is this? Because, well, couldn't I have really kind of almost skipped this step? All this does is change the unit. So it's really, that's one, I can almost like skip over that step. It was dividing by this molar mass and then multiplying by this molar mass. So if I want to think about it that way, I took this number and I divided by this molar mass. Then I used a 1-to-1 mole ratio, that doesn't change it. And then I multiply by this molar mass. So really it was divided by 50 and then times 100. Well, of course, that doubles your number. Okay, so then it's going to be that's a quicker way to do it if you think about almost like skipping this step because it's a 1-to-1 mole ratio. Think about skipping that step. Like a cookie cutter method is taking the number, whatever number's here, divide it by this molar mass, get the correct one, times this molar mass, and boom. And you can go through these much faster that way and fill them all in, including the one down here. You've got to complete all of these. This is the number you're going to be graphing. The number that you're going to be graphing on your graph, it's very important. So column F is what you're graphing. To get the percentage in the tablet, well, that's kind of easy. I still have this on my calculator. Well, it's F divided by the mass of the total tablet, which is B. So divided by 3.23. And then I got to put that in percentage form. So times 100 equals. And I probably round this to the nearest percent. It's about 28%. Percents are only so useful, so I'm just going to round it to the nearest percentage. Okay. So what that means is, what I used here was a little more than a quarter of the tablet. This has to be less than the tablet, right? Because that's the only source of sodium bicarbonate that we had. And you just see what percentage it is. But this is not what we're graphing. What we're graphing is this. And then when we graph it, well, we're going to put the volume of acetic, like 0 and 5, 0 and 5. And then, of course, it's going to be, each time you're going to be adding 5. So 10, 15, and so on. And then we're going to put the mass of sodium bicarbonate over here. Let's say 0.9. Let's say that's one that we get here. Let's say it gets bigger than that. Let's say it goes up to like 2.0 grams. So let's put like 2.0 grams here, 1.0 grams here. Whatever, you have to go a little bit higher than whatever your biggest number is. And then, well, we're going to see one of two things. We're either going to see this line kind of going up, 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 or sort of like going nowhere. So if it's going up, 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 what that means is, well, every time we added more acetic acid on the bottom, 5, 10, 15, 20, the reaction went up. That means the acetic acid would have been my limiting reactant. If you see this green line, it's the acetic acid. But, on the other hand, if you see it going nowhere, like up and down, not really trending in any direction, just pretty much flatlining, then that means no matter how much acetic you put in, didn't matter, because we were using up the sodium bicarbonate. So if you see a flat line, then this is the limiting reactant. If you see a slope going upward, a positive slope, then this one is the limiting reactant. That's how you tell in this particular lab. You're not going to be able to tell directly from your calculations because we only have numbers for one chemical, and that's actually the carbon dioxide. So by using the carbon dioxide, getting the moles of that, that's our key. We can unlock how much of this we used, and then we're going to see in each reaction, did we use the same amount? Did we use more? Which was the limiting reactant? And so on. So the Alka-Seltzer lab is a really good one for thinking about chemical reactions and determining a limiting reactant.